Good evening, everyone. My name is Flavia Pedone, and today I would like to present our work on developing a digital twin planning framework for road maintenance. We are all aware that our road network is essential for our modern society, as it enables connectivity, access to essential services, and it carries most people and goods. In order to keep our roads safe and efficient, maintenance is paramount. But the financial resources are, of course, limited, and this has led to a repair backlog in England and Wales that accounts for almost £16 billion. Compounding this, currently our road information systems suffer from fragmented frameworks and data silos, hindering interoperability and restricting the ability of local authorities to generate proactive planning insights. In this context, a digital twin can be seen as a very effective solution. A digital twin is a virtual representation of real-world entities and processes with synchronized bidirectional interaction at specified frequency and fidelity. Digital twins allow for continuous monitoring, performance degradation forecasting, what-if scenario analysis, and can provide a support for data-driven decision-making. But notwithstanding their many advantages, their large-scale adoption is hindered by the absence of widely accepted standards and methodologies. This is true especially for the planning phase, which is constantly overlooked. Addressing this gap, our research develops a raw digital twin planning framework in order to support more effective data-driven maintenance strategies and enable road authorities to transition toward these effective strategies. Our research methodologies was based on 4 phases. In the first phase, we wanted to understand what is the planning process. So to do this, we carried out a cross-industry analysis in order to derive a set of key steps that remain valid across diverse contexts. In the second phase, we investigated the planning processes of the 2 core components of digital twin systems. A digital twin system can be seen as composed of a physical asset, so in our case a road, an information system, and the bidirectional connection among the 2. So we investigated the literature reviews for road physical assets and information system, analyzing for roads the regulation and reports from road authorities, and for information systems the scientific literature on enterprise information system planning. In the third phase, we derived our raw digital twin planning framework by using compositional synthesis and analogical reasoning, and I will explain later better. In the last phase, we demonstrated the effectiveness of our planning framework through a real-world UK highway case study application. The results of the first phase, so of the cross-industry planning process analysis, is a general planning process that is composed of 5 key steps. These are: define the planning scope, understand the current situation, forecast future situation, define planning options, and prepare a project brief. In the second phase, building upon this general planning workflow that was identified in the first phase, we identified the key steps for the physical asset and the information system. We can see that the 2 processes are similar, but they present some differences, and the main difference is that the physical asset planning process is more project-oriented, while the information system one focuses mainly on satisfying the strategic organizational objectives. In the third phase, we derived our raw digital twin planning workflow by making a comparative analysis of the information system and planning process workflows. So we wanted to understand what were the similarities and different to decide which key step we could include in our workflow. To do this, we compositionally synthesized the steps, and to decide what to include, we used analogical reasoning. So if a step was common to the planning, physical asset planning process and information system planning process, then we deemed that it was to be included in the digital twin planning workflow. Otherwise, if it belonged to only one of the two core components, it underwent, the specific step underwent further evaluation. So if that step referred to a characteristic that was shared between the core component and the digital twin, then it was deemed to be included in the digital twin workflow. Otherwise, it was discarded. In the fourth phase, we demonstrated our workflow on a real-world UK highway case study. So as first thing, we identified the raw digital twin purpose and scope. The very first thing to do is to understand the primary motivation to develop a digital twin, because in order to be effective, a digital twin must be purpose-driven. In our case, the primary motivation was the fragmented information management system that was causing inaccuracies and suboptimal decision-making. The physical entities to be twinned in this case was a long segment of UK highway, and we twinned the assets as pavement, lighting, structure, and drainage. We identified the stakeholders and the necessary information requirements. Then in the second step, we assessed the current situation. To do this, as we can see in our planning framework, it is very important to get insights from stakeholders. So we carried out semi-structured interviews with 20 experts from the UK national highways in order to map the current pavement maintenance process. And we did this via an information delivery manual. Through these interviews, we could identify the challenges and improvements as the reliance on manual subjective methods for routine pavement maintenance and the significant system fragmentation. We therefore passed to the step 3, in which we forecasted the future conditions, and we also identified the desired future status. We did this always involving the stakeholders, this time through questionnaires, and we defined that the desired future state was to have a unified data environment that could help to retrieve information from these fragmented sources of information. In the fourth phase, we carried out a gap analysis between current situation and desired one, and we developed two main planning options. The first option involved a complete overhaul of the information systems, replacing all the legacy systems. And while this, of course, could be desirable in the long term, it requires extensive time and resources. Therefore, this option was discarded, and the second option was chosen, which proposed to maintain the existing information system and use an integration architecture that was able to retrieve data from these fragmented sources. We therefore, basing on the chosen option, defined the exchange information requirements and established the system requirements and specification, and proposed a 3-tier architecture that was based on these 3 layers: user access, federation middleware, and data source. The architecture proposed uses ontologies in order to retrieve metadata from fragmented sources while maintaining the existing information systems. This digital twin was a prototype, as I said, on a long segment of highway of a highway in England, and we tested it again against a lighting outage case study. In this case study, the system detects in the routine maintenance management system a lighting outage. Then automatically the system identifies all the concurrent assets and processes in order to see if there were interferences, and in this case it identified that there were some planned pavement resurfacing. Therefore, the system puts on hold this activity and prioritized the excavation necessary to repair the lighting outage, and then automatically changes the propagation once that the lighting outage has been repaired, and reschedules the planned maintenance activities. So therefore demonstrating the ability of this prototype to coordinate multiple teams across multiple systems. To conclude, our work provides contribution for both academia and industry. For academia, it provides a structured framework for the often overlooked planning phase that is based on evidences, and it is adaptable to diverse digital twin contexts through domain-specific tailoring. For industry, it represents a first step towards a comprehensive raw digital twin planning methodology that can provide an actionable guidance for road authorities to transitions to more effective data-driven maintenance strategies. We acknowledge some limitations that provide a roadmap for future work, and these are essentially technical scalability, because there is a need for further research on federated architecture and automated ontology that can work for larger road networks. Then a limitation is also refers to the validation scope, because currently we tested it against this lighting outage case study, but we want to test it on other use cases like the pavement degradation forecasting. And as last thing, we want to develop a closed-loop evaluation system in order to verify and ensure that the planning outcomes align with the strategic goals. Thank you for your attention. So the ontology was developed